In this video, we'll explore Dalton's law of partial pressures. And if you have not looked at any of the ideal gas law information or the introduction to pressure video, you'll want to stop right now and take a moment and watch those first before you tackle Dalton's law of partial pressures. So when we think about a mixture of gases, which is what Dalton's law is going to tell us about, it's helpful to think about something that's on a bigger scale. So I have this picture of a container of jelly beans, and we know that pressure comes from particles colliding with the sides of the container. And so we could say that the total pressure from this container has to come from the pressure of all the jelly beans, right? Well, those jelly beans aren't all the same color. So our total pressure here would come from the pressure from the blue jelly beans, plus the pressure from the green jelly beans, plus the pressure from the yellow jelly beans, plus red, orange, so on and so forth. Because each of those jelly beans is colliding with the sides of the container. So all of the pressure is coming from each of those individual colors. Dalton's law of partial pressures says that the total pressure is the sum of the pressures of all of the gases. So just like we had a mixture of jelly beans here, we can have a mixture of gas particles. And when we do that, hold on, I don't want to do that yet. When we do that, we're looking at P total, so the pressure on the container, which we've always just referred to as pressure up to this point because we just had one substance, but now we're going to start calling it P total. That's coming from the pressure of gas number 1 plus the pressure of gas number 2 plus however many individual gases I have. Now, these individual pressures will also have a new name. They are called partial pressures. So P1 will be the partial pressure of gas number 1. Great thing about the word partial pressure is you can continue to just think about it as it's the pressure of that individual gas in the mixture. So we could go back to our jelly beans and I could talk about the partial pressure of the orange jelly beans. Now, the partial pressure of the orange jelly beans is the same in this mixture as if I took all of those jelly beans out and put them in the same size container at the same volume and the same temperature. If these were all the orange jelly beans, the pressure on this container from the orange jelly beans would be the same as the pressure in this container from the orange jelly beans. So the orange jelly beans don't really care whether they're alone or whether they're with other jelly beans because they're still going to be running into the sides of the container and having the same amount of pressure. So let's look at an example. What is the partial pressure of argon in a mixture of argon and helium if the partial pressure of the helium is twice that of the argon and the total pressure is 300 millimeters of mercury? So this is one of those story problems where you kind of have to think about what you're being told here. I'm going to write down some of this information to sort of help me think of and sort out my thoughts. So it's asking for the partial pressure of argon, which I can just say, hey, they're looking for the pressure of argon. And we have a mixture. I'm going to draw a picture here to help me. We've got a mixture of some argon running around and some helium. And we know that the pressure of the helium is twice that of the argon. So the pressure of the helium is 2 times that of the pressure of the argon. And then we also know that the total pressure is equal to 300 millimeters of mercury. Okay, so now I can think about Dalton's law of partial pressure and know that my P total has to be equal to all the parts of my mixture. So that's the pressure from the argon and the pressure from the helium. I happen to know, because the problem told me, that the pressure of helium is equal to 2 argons. So I can substitute in for that pressure of helium. So I'm going to say that P total equals the partial pressure of the argon plus, I'm going to want everything in terms of argon, the 2 partial pressures of argon. So P total was 300 millimeters of mercury. Over here, I have 3 partial pressures of argon, so we can divide out the 3 and know that the partial pressure of argon was 100 millimeters of mercury. Let's look at another example. You have a mixture of equal amounts of neon, argon, and helium, and it has a total pressure of 150 millimeters of mercury. Some nitrogen is added to the mixture. After the nitrogen is added, we want to talk about what happens. So let's draw a picture here to help. I have my container, and it's got some neon running around in it, and it's got some argon running around in it, and it's got some helium running around in it initially. So this is my initial. So to start with, I have some pressure from the neon, and some pressure from the argon, and some pressure from the helium. And then, later on, we add some nitrogen to that container. So we mix in some N2. And I still have the same amount of neon, and I still have the same amount of helium. So now, what happens to the total pressure of the mixture from after I've added the nitrogen? Well, if you think about it, I have more stuff in here, and more stuff means more collisions with the size of the container, so my pressure goes up. So my P total increases. What happens to the partial pressure of argon? Well, if we go back and think about our jelly beans, it's like argon is an orange jelly bean, and it has a particular pressure associated with the argon molecules hitting the sides of the container. That pressure doesn't change when I add nitrogen to the flask because the number of argon molecules is the same, and the temperature is the same, and the volume is the same. So the partial pressure of argon stays the same, stays constant, doesn't change after I've added that nitrogen. If the amount of nitrogen that is added is equal to the individual amounts of argon, neon, and helium, what is the new total pressure? Okay, now we're going to have to do some math. So let's go back and look carefully at our problem. It says a mixture of equal amounts of neon, argon, and helium. So that tells me I have 1 argon for every 1 neon for every 1 helium. They're all equal to one another. And that if I add all of those together, it is 150 millimeters of mercury. So since argon and neon and helium are all equal, I can say that let's think about this. I can say that 3x, where x is my neon or my helium or my argon, is equal to 150 millimeters of mercury. And then I can solve for x. So x will be 50 millimeters of mercury, and that is the pressure of my neon and the pressure of my argon and the pressure of my helium. So that tells me that the individual pressures here were all 50. Each of those was 50 millimeters of mercury. The problem tells me here if the amount of the nitrogen that is added is equal to the individual amounts of what I started with, aha. So if these were 50 to begin with, and I'm adding nitrogen that's equal to what they started with, then I must be adding 50 millimeters of mercury of nitrogen. So my new total, pretty much here, I added 50 millimeters of mercury. Initially, P total was 150 millimeters of mercury. So if I add 50 millimeters of mercury to 150, then my new P total should be 200 Hg. And that's a pretty complex Dalton's law problem. So that's about as difficult as they're going to get.